Okay, in this section 3-4, we are looking at using zeros to find polynomials. Now in the last section, they gave us the function, the polynomial, and we had to come up with the zeros. So in this section, the problems are going to give us the zeros or some of the zeros, and based on that, we are going to have to find the polynomial function. So it's kind of like the last section in reverse as far as the problems are concerned. All right, so now what are we looking at here in this particular section? There's a lot of information we need to go through. The first thing that we come to are the fact that complex zeros occur in conjugate pairs. All right, complex zeros occur in conjugate pairs. And so what we need to look at here is this statement. It says, let f of x be a polynomial function that has real coefficients. So if a plus bi, and of course the b part is not 0, is a 0 of the function, then the conjugate a minus bi is also a 0 of the function. All right, so complex zeros occur in conjugate pairs. Right, so if you have one, then you've got the conjugate of it also as a 0. All right, another thing to note is that make sure that we understand that this only works for polynomial functions that have real coefficients. All right, so like here, both of these are real coefficients in the polynomial. All right, but it wouldn't work in this function, this g of x, because this is a complex, this is a non-real coefficient. This is an imaginary coefficient. All right, so just keep that in mind. Only works for polynomials with real coefficients. All right, so next thing that we are looking at here is talking about factoring a polynomial. So remember, linear factorization says you can write any nth degree polynomial as a product of linear factors. Okay, however, this includes the possibility that some of the values are complex, and so this theorem states that even if you don't want to get involved with the complex factors, then you can still write f of x as a product of linear factors. And so the theorem states this: every polynomial of degree n greater than 0 with real coefficients, right, it can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zeros. All right, so really what this is saying is, remember in the last section where we started getting some of the zeros, and some of the zeros were complex in nature? Well, what this theorem is saying is that as long as you have a polynomial with real coefficients, then if you don't want to deal with the complex factors, then they can be written as a product of linear and quadratic factors with real coefficients. The quadratic factors would just have no real zeros. And so really, if you think back to the last section where we had some real zeros and some complex zeros, so that means you'd have some real factors and some complex factors. Well, remember, the complex factors occur in conjugate pairs, so if you just multiply those together, then you would get a quadratic factor. So that's what this particular theorem is saying. All right, and so let me see here. So again, quadratic factor with no reals is said to be prime, right, or irreducible over the reals. And so a couple examples here of each one. So this one is irreducible over the reals because it can only be factored into a product of complex numbers. And so on the other hand, this quadratic is irreducible over the rationals, but it's reducible over the reals. In other words, you can't factor these into rational factors, okay, but you can factor it into square root factors. So keep that in mind. All right, so what kind of problems are we looking at? So here's the first example we want to look at. It says find a fourth degree polynomial function with real coefficients that has -1, and 3i as 0. So -1 has a multiplicity of 2, and then you have 3i. All right, now, okay, so let's think about this for a minute. Okay, this is a fourth degree polynomial. They've given us 3 of the zeros, and of course we know since it's degree 4, it's got one more. It's got one more 0. All right, and so what we want to start doing here is we want to take these zeros, write them out as factors. We'll be able to find the fourth zero, write that factor out, and then multiply it out to get the polynomial function. So let's try it. So I've got f of x equals, now here's the deal, it says find a fourth degree polynomial. That means there is more than one. Okay? And so what we need to do is we need to start by having an a out here, and then multiply that a times all of my factors. X plus 1, x plus 1, because the multiplicity is 2 there, and then x minus 3i. X minus 3i. Alright? Now, let's talk about what this last factor should be. So remember, this one is a complex factor, and complex factors occur in conjugate pairs. And so this is going to be now x plus 3i. Okay? And of course there's no, for this particular 0, there is no a component to that, right? Okay, it just has the b component, so that would just change from minus to plus right there. Okay? Alright, so now that we've got all of our zeros and we've written them out all as factors, then what I can do is, I can make my life a lot easier by saying, let's let a equal to 1. Because remember, it's asking me to find a fourth degree polynomial. And I can find different ones by plugging in different values of a. Well, I might as well let a be 1, because that makes my life a little bit easier. Alright, so again, I don't have to find all of them, I just have to find one of them. And by plugging in different values of a, I can find different polynomials. We'll let it be 1. And so f of x, since that's 1, it pretty much just kind of disappears. So let's multiply these first two together now and get x squared plus 2x plus 1. Okay, so let's multiply these two together now. And we're going to get x squared, disappears in the middle. And then so this is going to be negative 9i squared. But remember, what's I squared? Negative 1. So negative 9 times negative 1 is positive 9. Alright, so we've got that multiplied out. So now I have to multiply these two together again. So x squared times x squared is going to be x to the fourth. X squared times 9 is plus 9x squared. I said x to the fourth, but I wrote x squared. Let me change that to 4. Okay. Alright. Okay, let me see here. Where did I leave off? 2x times x squared would be plus 2x squared. And that'll be plus 18x. Now slide over with the 1 plus x squared plus 9. Alright, can simplify that a little bit more. F of x equals x to the fourth plus, let me see here. I've got an x, made another mistake up here somewhere. It's supposed to be x to the third. Alright, which is going to come next. Plus 2x to the third. Whoops, I might have said third and wrote squared. It's late at night, guys. Third. Okay. Now the next thing that I come to is plus. I can go ahead and put my squares together. 9x squared plus x squared will be 10x squared. Alright. And now I can go plus 18x plus 9. Alright, and so that is going to be a fourth degree polynomial function with these three coefficients. Alright? Now, let's move to the next problem. It says find a cubic polynomial function f with real coefficients that has 2 and 1 minus I as zeros, and f of 1 is equal to 3. Okay, so now let's talk about this part of it. What this is going to do is this is going to nail us down to one specific function with these characteristics. See, up here it just said find one of them, so I could let my a be whatever I want it to be. Here I don't have that luxury. I can't just find any one of them. I've got to find a specific one. And so this nails my A down to a specific value. I don't get to pick A in this problem. A is already picked for me because of this statement right here. So I'm going to have to find the A that would make this statement true. And we'll show you how to do that here in just a moment. But let's start off with f of x equals. Alright, so we've got A, and we'll open. So 2, that would be x minus 2. Close it off. Then I've got 1 minus I as a 0, so that would be, if I wanted to write that 0 as a factor, it would be x minus 1 minus I. Okay? Now, remember what we know about complex roots. Okay? If you've got a complex root, then the conjugate of that is also going to be a root. So that conjugate of this would be x minus open 1 plus I would be the conjugate. Alright? So I know now that these are my 3 factors of the cubic polynomial. So now we have a little bit of work ahead of us now to multiply this out. And so we'll just kind of do it one step at a time here. And so this A is just going to kind of hang out here in front, but I can now, let's see, what would be the best course of action for us to take here first? I would say that I'm going to go ahead and write this x minus 2 back, and I'm going to try to multiply these 2 sets of parentheses together. Alright, let's see what we get. So I got x times x, which is x squared, right? Okay, so now, here's the next thing that I want to do. Okay, I want to take x times negative 1 plus I. So that'll be my next one. I've got to write these out one at a time because I can't just simplify them like I normally would in my head. So that'd be x open, negative x open 1 plus I. Alright, close that off. Then I'm going to slide over and take this one. So that's going to be minus x. Alright, open, and then this one is 1 minus I, so it's not the exact same thing there. And then what I'm going to do is I'm going to take these 2 and multiply them together. So negative and negative make a positive, and then that's going to be 1 minus I close times 1 plus I close, and another close. Alright. So now, like I say, we've got a little bit of simplifying to do here. So f of x equals to a. Still not going to do anything with the x minus 2 yet. I'm going to try to simplify a little bit what I've got inside my parentheses here. So that's going to be x squared minus x minus xi, right? Minus x plus xi. Alright, so we've got that much done. Now I can go ahead and multiply this out. So 1 times 1 is plus 1. 1 times I is plus I. Negative I times 1 is negative I. And negative I times I is negative I squared. Okay, which is negative 1. Which I'm going to go ahead and write as plus 1. Why not? Alright, next step. F of x equals. Still just going to leave this a, still just going to leave this x minus 2. And so we're going to go ahead and see what else we can simplify inside this set of parentheses here. I can see that I'll take an x squared and just go ahead and put that there and cross things out as I go through them. Let me see, what else can we do here? We could probably go in and take a look at my x terms here. So that'd be negative x and negative x. So that's negative 2x, so we're good there with that. Let's see, what else we got here? Some regular numbers, 1 plus 1, that's 2. Alright, so let's see what else we've got. We've got a negative xi and then a plus xi and a negative I and a plus I. So those are gone. So really, now I'm down to here. So we're getting a little bit better here. So now I can go ahead and take this and multiply it out. And so x squared, that's x to the third, minus 2x squared, plus 2x, slide over now, the negative 2, negative 2x squared. Negative is a positive, 2 and 2 is 4, 4x. And negative 4 right there, that's what we'll have. And so, getting closer, still going. Sometimes there's no avoiding, you just have to actually keep on going till you simplify everything down. And so let's see what we've got here at this point. Now we can go f of x equals a times x to the third. We've got x squareds there, so that'd be negative 4 x squared. Alright, so we're good there now. Got those. Let's see here. What would come next? Plus 6x, I would say. Minus 4 doesn't have anything to combine with. Alright. Now at this point, remember what we said at the beginning. We're locked into this statement here. F of 1 has got to be equal to 3. We're going to use that to specify what value of a would make that true. And so the question is then, how are we going to do it? Well, into my function, if I plug in 1, okay, I've got to get a 3 out of there. So here's what we're going to do. We're going to say this. We're going to say a times, and in place of x, I'm going to shove in a 1. I'm going to shove in a 1 in place of all the x's here. So that'd be 1 to the third minus 4, open, 1, close, squared, plus 6 times 1, close, minus 4, right? And I need that to be equal to 3. When I shove in a 1 to the function, I better get a 3 out of the function for it to be correct. And so now all I need to do is solve this equation for a, and I will have the right value of a. And so let's see what we come up here with. So that'd be 1, and then that would be minus 4, and then that would be plus 6, and that would be minus 4. And so let's see what that all turns out to be here now. So that's going to be, let's see. Let's see. So that's going to be negative 8. That's going to be 7. So that's really just going to be negative a equals to 3. Well, if negative a equals 3, then a equals to negative 3. And then so now I've got the a that will make my function be what I want it to be. And so really now all I have to do is take this negative 3, plug it here, multiply negative 3 times every term, and then I will actually now have my answer. And so this is going to become negative 3x to the third. Negative 3 times negative 4 is positive 12x squared. And so negative 3 times 6 is negative 18x. And negative 3 times negative 4 is plus 12. And so now this is the cubic function with real coefficients 2 and 1 minus I as zeros, and f of 1 equals to 3. Alright, so again, the difference between this problem and the last one is in the last one, I got to pick whatever I wanted for A, and then that would give me a correct answer. Here, because of this statement, okay, they're forcing my A to be a specific value, and then I just have to use my equations to solve for the A, and then use that correct value of A to come up with the right polynomial that fits the characteristics of everything that's there. Alright, so that's kind of what we're looking at in this section, and so kind of take what we have looked at now and be ready for your quiz.